Welcome, class, to Unit 8, Cognitive Theories of Learning. We also call this information processing. It's about how the brain processes information. Today we'll cover types of theories, information processing in the brain, fMRIs, and implications of brain research in the classroom, including two categories: academic implications and executive functioning implications. So far, we've covered a number of different types of theories in the classroom. We've explored cognitive learning theories, social emotional theories, moral development theories, behavioral learning theories, social cognition theories, and so this week we turn to information processing theories, which focus on how the brain processes information. What is an information processing model? Well, we know that information constantly enters our mind through our senses. We see things, we hear things, we smell, we taste things. A lot of information enters into our minds and it's almost immediately discarded. Think about it. If you're walking down the hall during class change time, you're seeing hundreds of students. You might see a fight break out in your peripheral vision. You might hear girls laughing as they walk to class. You might see a student entering a classroom. You won't pay much attention to the large majority of this information, and so it'll be discarded. However, some information is held in our memories for a short time and then forgotten. Maybe the student entering the classroom reminded you of your sister, and so that might enter a different area of memory that we'll talk about in a minute and be retained for slightly longer. Tomorrow you might have forgotten that memory. Some information, though, is retained for much longer, perhaps for the rest of our lives. You see before you a diagram from the textbook. This diagram describes the information processing model for how information enters and is processed by the brain. Stimuli, such as the sights, smells, tastes, sounds, etc. that I've described, intersensory memory. Its capacity is only to hold about 3 to 7 units of information for about half to 3 seconds, and then most of it is forgotten. However, if we pay attention to it, if we focus on it, some of that information will go into working memory. Information enters into working memory at about 7 to 9 chunks of unit at a time. Without rehearsal, without trying to remember that information, most of that information is discarded or forgotten within 5 to 15 seconds. However, if we pay attention to that, if we rehearse that information can enter into long-term memory where it can be stored indefinitely. Think about some things that you learned either as an elementary student, middle school student, or high school student. Perhaps you memorized elements of the periodic table. Perhaps you know what a simile or a metaphor is. Perhaps you memorized a certain mathematical formula. If you remember that information now, it has been encoded in long-term memory. Let's see how that might have happened. At some point, your teacher taught you what a simile or metaphor was. You heard that information. You saw her write it on the board. That entered into sensory memory. You paid attention to it so it wasn't discarded. It entered into working memory. Perhaps your teacher had you practice identifying similes or metaphor. Perhaps she had you writing similes or metaphors. We call this practice and rehearsal. By practicing and rehearsing the information, that information was encoded in long-term memory. so that years later you can remember it and retrieve it back into working memory when you need it. How do we know this about the brain? We have heard as educators a lot about brain research and brain science. How do we know the things that we know about the brain? It's not enough just to take static X-rays of the brain. Scientists use what's called a functional magnetic resonance imaging, or fMRI for short, that enables them to observe the brain in action and has led to rapid advances in brain science. Think of this as a combination of X-ray or CAT scan machine and movies. Instead of just taking a static picture, areas of the brain are lit up and shown in real time as the participants whose brain it is shown images or slides. Scientists use this fMRI to study the anatomy of the brain and to understand how learning takes place. Now, why does all of this matter to you as teachers? Well, if we understand how the adolescent brain develops, we become more effective teachers for two reasons. First, if we know how information enters the brain and is retained by the brain, we can develop strategies that maximize learning. Think about it. All learning is getting information to be encoded in long-term memory. So it's logical to ask ourselves, what strategies can we use in the classroom that will enable information to be encoded into long-term memory? We can also understand how students make decisions, both poor and good ones. We call the area of the brain that makes decisions the executive functioning area. So if we understand adolescents' development in terms of executive functioning, we'll have a better insight into why they make certain decisions, both good and bad. One thing I want to dispel is that we know a lot of implications from brain research that we can translate into the classroom. You may hear a lot of brain myths, but the reality is we actually know very little that comes from solid, well-researched science about how the brain works that we can translate into classroom strategies. Here are some of the very few things we do know. First of all, we know that early stimulation leads to more learning, so that the amount of stimulation early in a child's development correlates with the number of neural connections, or synapses, which are the basis for higher learning and memory. We know if you take an infant and deprive it of stimulation, that child will not develop mentally the way an infant would that has a lot of rich stimulation. Rich stimulation can come in the form of smiles and touch, language and laughter, reading, songs, and more. We also know that more learning leads to greater brain efficiency. As a person gains in knowledge and skill, his or her brain actually becomes more efficient because more neural pathways are created in the brain. Finally, we know that not all learning is equally likely. Some types of learning are easier than others. For example, language and spatial relationships come more easily to young learners than advanced math concepts. This is another way of saying, at certain points in time, the brain is developmentally ready to do certain things. Think about Piaget. Piaget said that there were certain developmental stages that we all go through, and that learning does not precede development, but development precedes learning. This is another way of saying that the brain is ready to handle certain things at certain times. By the way, we know that the best time to teach languages is when a child is very young. His brain is plastic enough to be able to absorb many, many new words and syntax structures, and that gets harder as we get older. However, you wouldn't expect a toddler to be able to learn algebra, a much more abstract, advanced mathematical concept. So this is another way of saying that children, adolescents, and adults are developmentally ready to learn certain things at certain times. Now we know some things about adolescent brains that lead to two types of implications: academic implications, or strategies for how adolescents learn best, and executive functioning implications, or strategies for how adolescents make decisions. Let's discuss for a moment academic strategies in the classroom that align with brain research. Number one, we need to make learning developmentally appropriate for students' brains, which is what we were discussing on the previous slide. Number two, we need to make learning meaningful to students. Sometimes we use the word authentic to describe meaningful learning, and we'll talk about that in a minute. The reason that we want to make learning meaningful is that by doing so, students will be more likely to pay attention to it and to think it's important. If we can get students to pay attention and believe that their learning is important, they're much more likely to process that information from short-term to longer-term memory. And number three, we need to teach students how to become aware of their own thinking process. We call that metacognition. We call the strategies that refer to this as metacognitive strategies. And we need to teach them how to use study strategies to improve their learning. In this course, you are asked to do reflections on your assignments. Asking a student to reflect on their own learning is a metacognitive strategy, and the research suggests that it improves learning. Again, it probably improves learning because it helps transfer that information into long-term memory. Let's talk for a minute about what makes learning meaningful. What makes information meaningful? We said on the last slide that students are more likely to pay attention to information if the learning is meaningful. Information that makes sense and has significance to students is more meaningful than inert knowledge and information learned by rote. Rote learning refers to the memorization of facts or associations such as the multiplication tables, chemical symbols for elements, or words in a foreign language. It's not that we never teach rote information. It's that once we teach the rote information, it's better to apply that knowledge and information to meaningful tasks. Meaningful learning, in contrast to rote learning, is not arbitrary and relates to information or concepts learners already have. Let's take an example. Suppose, for example, you teach your students a formula for how to calculate the area of a shape. You can teach that formula, and you can stand at the board and write out area equals length times width. But it won't be meaningful to students until they've learned to apply the formula to something that has interest to them and meaning. For example, have them calculate the area of the classroom by measuring it and doing it that way. Give them different manipulatives with different shapes and give them inch cubes and have them figure out the length times width, the area. We're going to get into later in this semester two types of instruction: direct, which is a lecturing, and constructivist, which is where students figure out information on their own. Constructivism is more closely associated with making learning meaningful. Another way to make learning meaningful is to make it authentic. To make it authentic, ask yourself, what does a practitioner in my field do? For example, if you teach science, you might ask yourself when you're teaching a unit on pollution, you might teach your students the things that an actual scientist would do to measure pollution in a body of water. If you're so lucky as to have a pond at your school, you could gather the scientific equipment, go out and take some readings on the pond, and discuss the pollution levels in the pond with your students. Students could be encouraged to find out why the different levels came out the way they did. Perhaps there's a farm and there's some agricultural runoff in the pond. This is just one example of how you can make learning authentic and meaningful. Certain types of study strategies have been shown to help transfer information more directly from short-term memory to long-term memory. Study strategies such as having students take practice tests on the material, having students take notes, having them do selective directed underlining or highlighting, having them summarize information, having them write to learn, outlining, or concept mapping. All of these strategies force students to grapple with information, and when they grapple with information, they're much more likely to be transferring it from short-term to longer-term memory. Let's turn from the academic and talk about the executive functioning of the brain. We know that adolescents' brains are not yet fully developed. The brain doesn't actually fully develop until about the age of 25. And one of the areas that is underdeveloped is called the executive functioning center. This is the center that helps people make wise decisions. So because this isn't developed, adolescents are prone to risk-taking behavior. For example, putting themselves in physical danger, putting themselves in sexually advanced situations that they're not ready for, using drugs or alcohol, and other things. They're not always fully aware of the consequences. They don't know that terrible things can happen to them if they make really poor choices. They don't know that they're mortal. They want to explore, so they go out and sometimes do risky things. They also want to go along with the group, and so they feel a lot of peer pressure. They are more distressed than adults when rejected by peers. The perfect storm of this is when you have a group of adolescents at a party and they're drinking or they're high, and someone says, let's take the car out for a ride. If they manage to get their hands on the keys, I've seen more than one tragedy result from that. Later, when you talk to the survivors of such a tragedy, they'll say, we didn't think anything like this could ever happen. So adolescents are prone to risky behaviors, and they're not always fully aware of the consequences because their brains don't fully mature. What can be done? As a teacher, you're responsible for more than just teaching your students information. If you see risky behaviors, you must do certain things. First of all, try to turn your students onto healthier, safer risk-taking choices. Ziplining, for example, comes to mind. Sometimes, though, adolescents are participating in those behaviors simply because they want to feel that they are part of a group. There are many ways to feel that they're part of a group other than participating in any risky behaviors. Sometimes if you can connect that adolescent to an appropriate extracurricular activity, they'll feel like they're a part of a group. Drama, band, chorus, art club, math club. There are many extracurriculars in many schools. Second, point out the consequences of risky behavior. Make sure you clearly describe what could happen if they did something or what could have happened if they did something. Third, involve students in safe extracurricular activities to make social connections. We've talked about that. And finally, stay informed and as involved in their lives as they will allow. If you hear of particularly risky behavior, of course, it is incumbent to alert the parents and possibly the administration, depending on what the behavior is. Here is a summary of this lecture. Information processing focuses on how the brain processes information. The information processing model describes how information enters into the brain's sensory registers for a few seconds and is either discarded or processed into the working memory, and that's either discarded or processed into long-term memory. Paying attention to the information and rehearsing the information increases the likelihood that it will enter long-term memory. We call this process encoding. Our knowledge about brain research in relation to the classroom is limited. However, we use fMRIs to help us understand some useful information. Academic implications of brain research include that we need to make learning developmentally appropriate, we need to make learning meaningful, and we need to use metacognitive study strategies. All of these help transfer that information and encode it into long-term memory. Finally, we learned that executive functioning in adolescence is not fully developed because the brain is not fully developed. We need to point out consequences of behavior and offer safe alternatives. I hope you have enjoyed this lecture.